Okay, then we're looking at tutorial 1, question 1. We have a simply supported beam with a uniformly distributed load, total load of capital W, where the convention is capital W equals lowercase w times L. So whereas small w would be in, for example, kilonewtons per meter, so force per unit length, therefore we have to multiply it by a length to get the total load W. So we've been given the total load of W, so R1 and R2 must be equal because everything's symmetrical. So R1 equals R2 equals capital W divided by 2. Okay, so for the shear force then, which we will draw as V, we will come to a negative W divided by 2 and a positive W divided by 2, and then we will get some line, because it's a UDL, that is linear. So if we take a section here, for example, we've got R1 minus some length of W, and when we get to halfway, the length of W is W, or the magnitude of this part of the load is W divided by 2, so we get W divided by 2 minus W divided by 2, which brings us to 0 at this point, the center point here. Okay, and then we come down linearly to minus W over 2 at R2. Okay, so that is our shear force. Shear force diagram. If we were giving that in terms of small w, so force per unit length, then that would be minus WL upon 2, and this would be WL upon 2. Okay, because WL is equal to capital W, which is the total load. Okay. Similarly, we know for our bending moment diagram, we will draw that positive downwards. By convention, we draw that on the tension side. So because it's a UDL, we get a parabolic. Not drawn that terribly well, but that is a parabolic curve. And we're interested in the maximum bending moment at mid-span. So if we take the reaction, R1 is capital W divided by 2. And we're taking a section at mid-span, and we want to find the internal bending moment M. We have a remaining force which is half of the total W, so that's W divided by 2, and we can say that that can be considered as acting, if we integrate it, the average lever arm is L divided by 4, so where this is L divided by 2. Okay, so this moment is made up of a clockwise moment given by this reaction at its lever arm, which is capital W divided by 2 multiplied by its lever arm, which is L divided by 2, and then we subtract the anti-clockwise moment, which is given by the UDL itself, which is W divided by 2, and that's multiplied by its lever arm, or its average lever arm, which is L divided by 4. So we get WL divided by 4 minus W, make sure that's a clear capital W, WL divided by 8, which gives us capital WL divided by 8. So our maximum bending moment here is WL divided by 8. Okay, so that is our bending moment diagram, we have to come to 0 at each of these supports because we're not capable of generating an external reaction moment. So this is our shear force diagram and our bending moment diagram. And if we were to represent that in terms of the small w, lowercase w, which is the force per unit length, then we would have to multiply that by another length, so we'd have WL squared divided by 8. So you may see that in some texts as the moment is equal to small WL squared on 8, or the moment is equal to the total load multiplied by the length divided by 8, depending on which textbook you look at. Some of them will give you them in terms of lowercase w, some of them will give you in terms of uppercase w, where uppercase w is small lowercase w times the length. Okay, that's question 1. In the next video we'll look at tutorial 1, question 2.